Thank you for joining us for today's webinar for code officials. My name is Ben Zong and I'm with Frontier Energy. A couple of administrative items before we get started. Everyone is muted. However, we do encourage you to ask questions by using the GoToWebinar tool. Also, these slides will be available later this week. Today's presentation is part of a US DOE-funded education and outreach program to advance hydrogen and fuel cell electric vehicles in the Bay Area and beyond. The program is managed by the City and County of San Francisco Department of Environment in partnership with the presenting organizations. Today, we have two presenters. The first is Gia Vasson. She's the ZEV Infrastructure Project Manager with the California Governor's Office of Business and Economic Development, or GoBiz. Our second presenter is Jennifer Hamilton. She's the Safety Education Codes and Standards Project Manager for the California Fuel Cell Partnership, or CAFCP. And with that, I will hand it off to Gia.
Okay, so GoBiz really exists to serve as California's single point of contact for economic development and job creation efforts. And the unit that I'm in, the ZEV Infrastructure Unit, our mission is to accelerate deployment of infrastructure and market growth in order to achieve Governor Brown's goal of reaching 1.5 million ZEVs on the California roads by 2025. Next. So since his first day in office, accelerating zero-emission transportation has been a pillar of Governor Brown's administration and in our efforts to reduce greenhouse gases and improve air quality. And so in 2013, Governor Brown released the first ZEV action plan, which essentially was just like a to-do list for state agencies to take actions that were within our control that could help accelerate ZEV adoption. And in just 3 short years, we realized that the market had really evolved significantly and agencies had been completing many of the actions that were outlined in the 2013 action plan. So in 2016, October of 2016, an updated version of the ZEV action plan was released. And there were a few key differences that I want to point out just to kind of illustrate how things changed in just a short amount of time. So the plan now includes medium and heavy duty sectors, which of course is a key area in reducing criteria pollutants and greenhouse gases. It also focuses more on increasing accessibility of ZEV technology, so everything from kind of car sharing to public transportation to access to infrastructure. And the plan now includes 2 new sections, which is growing ZEVs beyond California and leading by example, which is basically setting targets for state agency fleets to increase the number of ZEVs in their fleet. And the other sections of the plan are similar, just kind of enhanced versions of the 2013 plan. So a full action plan is available on a number of different sites, and it's really easy to find. If you do a quick Google search for ZEV Action Plan 2016, you'll be able to find it. Next slide. So I want to talk a little bit about station development and how far we've come. The state recognized the need to get infrastructure in place in order to catalyze the market and really send a signal to industry that California was committed to this technology. So less than 2 years ago, if you look at the bar chart on the right, October 2015, we had just 2 retail stations open. So the blue bar at the bottom is open retail stations. You can see these other colors of where in the process of development different stations were. We had just 2 retail stations open. About 6 months later, I guess, in April of 2016, we had 15, which is a huge jump. And just over a year later, that number is nearly doubled. And next slide, thank you. We have now 28 open retail stations open. There are 25 others that are awarded with Energy Commission funding, and I'll talk a little bit more about that in a minute, that are in different stages of development. And there are 7 more stations that have proposed funding, which once they're approved by the Energy Commission, will move forward, which we hope and anticipate will happen in August. Next slide, please. So I just want to let you take a look at this map. I'm going to talk a little bit about where the funding is coming from the state. So just to show you this, the Fuel Cell Partnership actually produced this beautiful map, and it shows, here's the Northern California, so we'll stay on this for a minute so you can have a look. the green are the current open retail and other here in Emeryville. There's a station that's not a retail station that's open, and then the yellow ones are those that are in development. So you can see some in the South Bay and some in the East Bay, and then the purple are those that are proposed that were just awarded proposed awards from this last round of funding. And now, as this is Southern California, we'll I'll let you have a look at this while I share a little bit more about where funding is coming from. So the majority of this momentum, I think, was really catalyzed by investments by the state. So the Energy Commission provides up to $20 million a year through 2023 to co-fund at least 100 stations. And the idea is that this should really enable private investment in the market to kind of launch the market further. So to date, the Energy Commission has earmarked $136 million for hydrogen refueling stations. And I think there's a great example of how this has been changing in such a short amount of time. So the last funding opportunity that awards were, which is the purple dots on here, the proposed awards were released in February, was hugely oversubscribed. There was $33.4 million available from the Energy Commission, and $216.7 million were requested in funding, with nearly $90 million in private capital on the table to help build the network. So that really shows that this is moving forward and that the momentum is growing and building. And let's see, next slide. So I want to spend just a couple minutes talking about why fuel cell electric vehicles, and Jennifer later will talk in more detail about the technology, but just to give a higher overview, fuel cell electric vehicles are really we see them as a very important complement to the battery electric vehicle market and really key in helping California achieve its ZEV goals. They offer a long range, upwards of 300 miles per fill, and they have similar to a gasoline vehicle, fast refueling, 3 to 5 minutes, and the only emissions from the tailpipe are water, quieter than a gasoline fueled car. And next slide. And we have the cars, they're here. There are commercially available vehicles right now. So this, the top left here shows the Honda Clarity, and the bottom left is the Toyota Mirai. We have on the bottom right the Hyundai Tucson fuel cell vehicle, and then the top there on the Mercedes is their fuel cell vehicle that will be, we anticipate release sometime in 2017. Next slide. So I mentioned these already. The point of this slide really is to show that the Tucson and the Clarity are leased vehicles. The Mirai can be leased or purchased. And then again, here's the Mercedes-Benz expected in 2017. The other major auto manufacturers have indicated that they plan on having a fuel cell vehicle platform in the not too distant future. The other benefits of this, $5,000 rebate on the car, you get a carpool sticker, and right now the fuel is free. So $15,000 or a free fuel, or 3 years of free fuel. So there's some great benefits. Next slide, thank you. And it's actually more than cars. So it's not just passenger vehicles. Unlike new batteries, fuel cells really offer an increased potential for larger vehicle applications, SUVs and crossovers and trucks. And there are other forms of applications too here. So you'll see in the top left, the forklift. I think it's a great indication. Amazon just made a large investment in a fuel cell company and they'll be using fuel cell forklifts in their warehouses. The bottom right, you see the Chevy Colorado can be potentially used for military. There are plans just above that. You see a concept for a passenger ferry in the San Francisco Bay Area, which is gaining some traction. And there are also opportunities for fuel cell streetcars and locomotives. You see there in Sacramento. There are demos for longer haul trucks, medium duty, and heavy duty, so long haul and package delivery trucks. One picture, image on here that I realized is missing that's very important. I just want to take a minute to talk about our buses. We have fuel cell electric buses. Four California agencies are operating them. So 3 transit agencies and 1 university in Southern California. And there's a long history of experience and performance data here. They refill similarly to natural gas and diesel, and one hydrogen station can really provide the fuel needed for a local fleet. Next slide, please. All right. Now Jennifer is going to talk a little bit more about hydrogen fuel cells technology.
Thank you, Gia. So a little bit of background on hydrogen for those of you who aren't familiar. Hydrogen is not new. It's an industrial commodity and been used in a variety of industrial processes with a really decent safety record for decades. This slide includes just sort of a laundry list of some of those processes. One of the major ones being petroleum refining. So the gasoline that we put in our vehicles is essentially, for lack of a better term, cleaned up with hydrogen. And you see there that there's quite a volume of hydrogen produced globally. And because it's in such high use and production already, and for decades, it's also been transported, again, with a fairly good safety record. And there's a few different ways of transporting it. The top right image there is of a liquid hydrogen truck, which can deliver hydrogen to a fueling station, or in this case, you see NASA and the space shuttle in the background there. NASA has quite a bit of experience with hydrogen and liquid hydrogen specifically. There's also gaseous tube trailers in the lower right corner. And again, stations can have hydrogen delivered in that form as well, and we'll talk about that more in a moment. There's also hydrogen pipeline. Again, that's with the refineries. And in Southern California, the Torrance pipeline station is actually hydrogen off of an existing Air Products pipeline, again, for a refinery. So we'll talk more about how stations are designed, but you can see from, or hear from this, that there's not one way to do that. So where does this hydrogen come from that's produced so much? Currently, and the way they've been doing it for decades, is by reforming natural gas. It's called steam methane reforming. And that's pretty much how we're seeing it currently, although moving towards the renewables is definitely the overarching goal and kind of the gold standard for hydrogen. And that's using renewables like wind or solar to generate the energy that's required to make the fuel, and every fuel requires energy to make, as well as a renewable source for the hydrogen itself, such as biomass or digester gas at a wastewater treatment plant, for example. So one of the benefits of hydrogen is promoting the energy independence and energy security by using local resources and potentially renewable resources for its generation. So some of the properties of hydrogen that make it different from other more common fuels, but in some cases more advantageous. First of all, hydrogen exists as a gas at ambient temperature and pressure. When it's a liquid, it has to actually be at a cryogenic temperature, which is -423 Fahrenheit. So pressurizing the gas to put into either a tube trailer or into a vehicle, as you'll see, does not liquefy the hydrogen. It has to be at -423. Liquid hydrogen storage is at low pressure, and that is in a vacuum insulated double-walled tank that relies on the cold temperature to keep it liquid. So you do have boil off and associated pressure vents and so forth with that type of storage. The gaseous storage we'll be talking about is at pressure, and we'll talk about that more in a moment. We talk about hydrogen in kilograms, and it's metered by weight. If you were to burn, though, a kilogram of hydrogen and a gallon of gas, you get about the same energy in BTUs. We're not burning the hydrogen in the cars, but you can think of the volume of energy that the cars hold in gallons of gas equivalent. So a kilogram of hydrogen is about equal to a gallon of gasoline in energy. So let's talk about some more of the properties of hydrogen. It's colorless, odorless, and non-toxic. It's not odorized like, for example, natural gas for a couple of reasons. The first being that because hydrogen is such a small molecule and so light, it's 14 times lighter than air, finding an odorant that would stay with it as it rises and dissipates should it leak is problematic. But more importantly, for the fuel cells that the cars and buses and all those other applications use, The hydrogen has to be almost 100% pure. And there's actually an SAE international spec for fuel quality for the light duty vehicles and buses that require the hydrogen to be almost 100% pure. So we really can't have anything else in the hydrogen for the sake of the fuel cell. It is more energy dense by weight, and again, it is metered by kilogram. So a kilogram of hydrogen at atmosphere would actually occupy about 423 standard cubic feet. So in order to get enough energy on board vehicles so that you and I as consumers can get the range we expect that Gia noted earlier of 300 plus miles, we do need to pressurize that gas for storage on the vehicle. And we'll talk more about that again in a few moments. Hydrogen is flammable. It wouldn't be a fuel if it wasn't, and you can actually combust hydrogen, but we're not doing that. We'll see how it works in just a moment. A couple of points to make on this slide are that the safety systems that are employed for hydrogen are going to be able to detect and alarm a gaseous leak at levels much lower than that lower flammability limit of 4.1%. So while we don't want to have a hydrogen leak, should one occur, there are gas sensors that are employed in vehicles, at stations, and in repair facilities that would detect an alarm at levels around 10% of that LFL, so about 0.4% hydrogen in air. And if those leaks were significant enough to reach concentrations of around 2% hydrogen, systems are ultimately designed to shut down and isolate themselves. For example, if one was fueling at a station and a leak was detected in the dispenser cabinet, that station would be able to stop the fueling, isolate the various processes within the station, and shut itself off safely. The most easily ignited mixture of hydrogen, which takes the least amount of energy to ignite, you can see is quite a bit higher than those other fuels. And for gasoline, we're referring to the gasoline vapor. Hydrogen, if it is ignited, a pure hydrogen flame can be difficult to see, especially in daylight. However, if there's other fire around and the hydrogen that's the ignition source, then those other products of combustion are very likely to give hydrogen a flame color. Also, the radiant heat from a hydrogen flame is much lower than another carbon-based flame. However, the internal flame temperature is quite hot. So let's talk about how the hydrogen is used and how the fuel cell works. These cars are generating their own electricity in real time using the hydrogen that's stored on board the vehicle in a fuel cell, which is an electrochemical device that's essentially borrowing the electron from the hydrogen molecule to generate the electrical current. The proton passes through a membrane in the fuel cell, and all of those come back together on the other side of the reaction to form water as the byproduct. So these vehicles, or forklifts, or buses, or whatever application we're talking about for transportation, they are electric, but we don't plug them in. We go and fuel them at a station similar to gasoline, and they are hybrids because they have a fuel cell and battery for power. However, the fuel cell would be, in most cases, the primary power source for the car. And all of the cars will have essentially the same components in terms of a fuel cell, a high voltage battery, an electric drive motor, fuel storage, and just where those are placed on the car will depend on the different manufacturers. So for comparison's sake, that was a Toyota Mirai. This is the Honda Clarity. And you see that in the Clarity, their drive batteries in the center, and they've put their fuel cell stack under the hood. In general, the fuel storage will be towards the rear of the vehicle. So let's talk about the onboard hydrogen storage for a moment. These are, again, pressurized gaseous cylinders. The light duty vehicles currently store hydrogen at 70 megapascals, or approximately 10,000 PSI when they're full. Buses, forklifts, and some other applications might use hydrogen at 5,000 PSI, or 35 megapascals. There's also high voltage system as other hybrid vehicles already on the road. And those are indicated by orange wiring per SAE International standards. Anything over 60 volts is considered high voltage. And these systems, just like what's been on the road for decades now, do have safety systems associated with them in the form of self-monitoring or ground fault monitoring. There's inertia switches that, in the instance of a collision, the system isolates itself. And essentially, there are safety systems that are associated with the unique properties of these cars, in addition to what's already on a car. So there are solenoids in the fuel system that are electrically activated and whose default position are shut. There are relays in the high voltage system that are electrically activated and whose default positions are open. And in the event of a safety incident like a gas detection or in a collision, or even in normal operation, these will, when they don't have a 12-volt signal, are designed to isolate the fuel and isolate the high voltage to the battery. I mentioned before we don't want a hydrogen leak, and the whole goal is to keep fuel in the tank. But the reason that a car would need to vent is in the case of a fire. And in that case, each tank is equipped with a thermally activated pressure release device whereby it will melt open, the fusible plug will melt open and vent the contents of the tank. But again, in just your typical everyday normal operation, isolation of the fuel and high energy occur on shutdown of the vehicle. And as far as the onboard fuel storage, these tanks are very robust. They are designed and constructed in accordance with industry standards, and they are also tested in accordance with safety standards as part of design qualification in a batch form. So the standards include SAE, ANSI, and the global technical regulations for hydrogen and fuel cells, which will be adopted by NHTSA as the fuel cell vehicle FMVSS. The whole point of this testing is to ensure that these tanks vent and we don't have rupture. And those tests include things like a projectile test. Essentially, they shoot the tanks. There's a bonfire test, as well as environmental tests and drop and pressure cycling, hydrostatic testing. There's a whole list. And additionally, these vehicles do have to go through safety crash testing, just like any commercial vehicle on the road. So in talking about stations, I mentioned earlier, there's not one way to do a station, and you'll see that here. We can make hydrogen on site using an electrolyzer and water, or with a natural gas reformer like they do in industry, just on a smaller scale. What we're seeing mostly is delivered hydrogen, and that's either in the form of liquid and stored as a liquid on site, or as gaseous hydrogen, either through the pipeline, as you saw, or those tube trailers. Every stationary facility will have the required NFPA 704 placarding to identify if you have gaseous and or liquid hydrogen. And there are safety systems that are employed associated with high pressure storage and so forth. So just to note that, not every fuel is inherently safe, and hydrogen, again, is a fuel, the vehicle fuel. And so it's really those systems that are designed around the properties of the fuels that allow us to handle them safely. And so hydrogen, just like other fuels, when it's handled properly, is just as safe, if not safer, than gasoline that we're very used to, or natural gas or propane. So you see in these photos, there's examples of ASME steel pressure vessels and ASME composite stationary storage for higher pressure storage at fueling stations. We do have the associated safety systems employed in the form of pressure relief devices and valves, safety vents, as well as fire and leak detection systems. The stations do go through engineering and safety, HAZOPs or FMEAs. There's also materials compatibility that's cited, and so we don't want to cause materials to become embrittled by hydrogen, so all of the material that comes in contact is hydrogen compatible. And there's other systems that you would expect to see with gas stations, like emergency stops and bollards, breakaways are required, etc. When we fuel the vehicle, these are the nozzles that attach to a receptacle on the car. So for 35 MPa or 5,000 PSI, there's a specific nozzle that is actually got different geometry than the 70 MPa nozzle. So while you could connect a 70 MPa nozzle to a 35 MPa receptacle, you cannot do the opposite. And these nozzles, lock on, and the station will actually perform they'll pressurize the hose and perform a check and make sure that everything's connected properly, no leaks occur before it starts the fueling process. And during the fueling, the station is required by code to perform 2 leak checks during that fuel process. And if it detects leakage, then it will stop the fueling process. So here's a schematic of a car connected to a hydrogen dispenser, just a generic one. So it's not really too different than what we're used to seeing with gasoline in terms of it's a dispenser with a point of sale and a readout. There's a hose with breakaway. You see the nozzle there. A couple of additional features are temperature sensors, because temperature is an element of fueling, and there's also a cooling block. Hydrogen actually, rather than cooling on expansion, it heats up. So in order to get that 3 to 5 minute fueling, the gas is pre-cooled before being dispensed into the vehicle. So Gia and I are going to tag team this next section a little bit, and I'm going to turn it over to Gia to start talking about hydrogen station permitting.
Thanks, Jennifer. So the GOBIZ produced a hydrogen station permitting guidebook, and the guidebook provides information about the permitting process and suggested best practices for local and regional governments and station developers that are seeking to open or in the process of opening hydrogen stations. So here it's kind of an overview of the sections of the guidebook. It includes information about the importance of hydrogen for transportation in California, the hydrogen properties and the production of hydrogen, talks about fuel cell technology and benefits, so kind of an abbreviated version of some of the things that Jennifer was just talking about. It provides information and diagrams about the different station components and the setup of a station and the sale of hydrogen in California. Now, the permitting process has 5 main phases, which are listed here: pre-application outreach, planning review, building review, construction, and commissioning. And so the guidebook kind of breaks each of those down and walks through what you can anticipate what will happen during that phase of the development, and so forth. So next slide, please. So the beginning of the guidebook also provides a handful of checklists that help the AHJs and developers think through some key questions that can be answered to help streamline the permitting process. So here is an example of one that's tailored specifically to the local jurisdictions, and these are the questions that you might want to think through when being approached or thinking about permitting and planning and developing a station. You know, we recognize, of course, that every jurisdiction is different, and so we always strongly encourage developers to engage the local officials really early in the process and really understand what's going to need to be happening at the local level. And I just also want to point out that the guidebook at the end, there's a series of appendices that provide some other helpful information around codes and standards, different setback requirements. There are vehicle diagrams. There's an example building permit in there, and a list of kind of relevant, helpful organizations and different contact information for that. So you can find the guidebook on the GoBiz website, which I think will provide the link to our website, I think, in our contact information. Okay, next slide. Thank you. So I just wanted to quickly point out that there are 2 key codes for hydrogen station development. The California Fire Code and the National Fire Protection Association, or NFPA 2. Of course, other California building codes like electrical and mechanical codes would apply here as well. These are the key codes for hydrogen station development. And I mentioned the appendices of the guidebook before. A kind of more complete list of relevant codes and standards is in Appendix A of the guidebook. So you could kind of look through the different codes that you might want to be aware of depending on the specifics of the project in your jurisdiction. Next. All right, so CUPA applies to state and local agencies or private entities that require some discretionary approval. And currently, I'm hearing a little bit of feedback. Sorry, are others hearing that too?
No, not on this end.
Okay, good. Okay, no problem here then. So currently all hydrogen stations are built on existing gas stations, so that doesn't trigger a CEQA review. And additionally, several jurisdictions have filed a categorical exemption, or they prepared a negative declaration. So CEQA.net lists the CEQA categorical exemptions that were filed by the California Energy Commission to encumber the funds for the hydrogen stations that are being provided through the grant funding opportunities.
So for those of you who are familiar or are the Certified Unified Program Agency, just wanted to cover this a little bit. We've talked to some hazmat folks about this previously, and every hydrogen station will require a hazardous materials business plan per the California Health and Safety Code and the Code of Regulations. And in that business plan would be the inventory, fire code compliance, what training and documentation there is, and so forth, just like any other hazardous materials business plan. The other applicable CUPA program element is, of course, the fire code, and there's just a laundry list here of some of the sections that apply. And now that the Office of the State Fire Marshal has adopted by reference NFPA 2, Chapter 10 is on hydrogen, gaseous hydrogen fueling facilities, and so that would also be something to take a look at and something that station providers are using as a design criteria. Non-applicable CUPA program elements include CalARP, and we address this because it has been a question in the past. But essentially, no hydrogen station currently has meets the threshold quantity for on-site storage of hydrogen, which is 10,000 pounds. Even at a very large station of 2,400 kilograms, which we don't even have yet, that would still be about half of the threshold quantity. So it's not to say that someday, and we'd like to think someday, we'll have these larger stations potentially, but right now they do not meet that. Other non-applicable program elements include underground storage tanks. Again, that might change someday, but currently all of the equipment and the storage is above grade. And obviously nothing with petroleum as far as hydrogen is concerned, even though these are at existing gasoline, many of them are at existing gasoline stations. And then also the hazardous waste treatment and storage disposal is not required, as there is none associated with the operation and maintenance of a hydrogen station. So I'm going to talk quickly about some resources that are available to you. And the nice thing is we have kind of a one-stop shop. There's lots of us in the hydrogen industry, and we're all happy to help. But this h2tools.org, we've got listed on quite a few websites, as it does have quite a few resources in one location. This is managed by the Pacific Northwest National Laboratory. And you'll see on the top right a list of the user groups. So it's really meant to be a resource for anyone from folks like yourselves, the AHJs and code officials, to first responders, to project proponents, and even the general public. And it covers things like, of course, codes and standards. There's information on some of the other projects within DOE, like H2 First. HiStep is the device that's used to validate or to prove out station performance as a part of the commissioning process, materials compatibility, and so forth. So a couple of things to highlight. This is a fairly new publication, the Hydrogen Equipment Certification Guide. Within the fire code and even in NFPA 2, there are several places that say that the requirement is that the items be listed, labeled, certified, or approved equipment. And so that approval is actually employed quite a bit because, unfortunately, right now there's not a lot of listed and labeled equipment. There's some, and it's getting better, but we're still moving toward that. So the approval process is really what's happening, and this guide is meant to help with that. Other things you can find on here are lessons learned, and there's also a best practices page for hydrogen, not specifically on stations or just about stations, but just kind of hydrogen in general. But I invite you to have a look at that. Another resource that's not listed here, but I'll mention, is the Hydrogen Safety Panel. They've actually been pretty instrumental in this last round of funding or of proposed awards and working with the Energy Commission and helping to review some of the safety plans for those stations. And just mentioning this to you so that you know that it's available, not so much for AHJs or someone approving an application, but more for the engineers and the station designers, is the hydrogen risk assessment model, where they can input information and have a very fast output of a risk assessment for the various design elements of their station, like pipe diameter or tubing size or things like that. If I put a valve here or take a valve away there, how does that risk change? So that's something, again, developed by Sandia National Laboratory and housed here on the H2 tool. So I do invite you to please have a look at that. Nick Barillo is the manager of that site, and he is also manager of the hydrogen safety panel, and I'm sure happy to answer any questions as well. Ben?
All right. So before we get to the Q&A section, I just wanted to note again that if your phones are muted, but you can use the GoToWebinar tool to ask questions. Again, thank you for joining us for today's webinar. This presentation is part of a US DOE-funded education and outreach program to advance hydrogen and fuel cell electric vehicles in the Bay Area and beyond. The program is managed by the City and County of San Francisco Department of Environment in partnership with the presenting organization. So we have one question so far on the webinar, and that's, I think, Gia, you may have already answered this, but will the permitting guide be available, and where can they find it?
Yes, it is available. You can find it on the GoBiz website, which is business.ca.gov. And then there's a section on the zero emission vehicle unit, and you'll find it there on our resources. And we can also add, a more specific link before we send these. I think we're going to make these slides available. We can modify that to make it easier to find.
All right, second question. How can you provide help for local jurisdictions, and what kind of additional help?
Well,
so
I'll let you address that, yeah.
Yeah, I'll address that. So we're really here to help answer questions that arise. There are a number of ways that our unit is really intended to help you navigate challenges that are coming up. If a station developer is needing some assistance connecting with a local jurisdiction, if there are ways that we can help connect with the utilities to move a project along. Really, I think that if there are things that are coming up that you think assistance from the state may be helpful in, don't hesitate to reach out to us, because we've done a lot of different things, from convening meetings, from sending emails, from coming out to the site and helping to troubleshoot with you. So I think that if there's something that comes up and you think we might be able to help you, we certainly can. And if we don't have the answer, we will most likely be able to connect you with somebody who will be able to help you solve the problems that you're running into.
Absolutely. And I'll just say that, the hydrogen community is fairly small, and we are all in this together to see this succeed. And so, the resources are out there. Please feel free to reach out to any of us with questions, concerns, and we can certainly get you in touch. If we don't have the answer, like Gia said, we can point you in the right direction to the folks who do.
Yeah. Okay, thanks. So those were the two questions we had. Again, if you have any questions later on, the San Fran environmental staff are available to provide technical assistance to AHJ staff and station providers, and to organize community awareness events in the Bay Area jurisdictions with proposed hydrogen fueling stations. For more information, please contact Suzanne Lucen at SF Environment. And also, these slide decks will be available again later this week, as well as the recording. You're going to receive 2 emails after this webinar. The first one is going to come probably within the next day, and that's more of a survey for feedback. The second email later this week will have the details on where you can get the recordings and the presentation. So with that, thank you again, and have a great day.